All right. Having covered Actor-Critic, in the next portion of today's lecture, we will actually further build on this idea of value functions and Q functions to develop algorithms that don't require an actor at all. And the culmination of this will be to get to what are called Q learning methods. All right. So the question we're going to ask here is, could we actually omit the policy gradient completely? Can we do reinforcement learning entirely using value functions? So remember that our advantage, A pi SA, tells us how much better is an action A than the average action according to pi. The argmax of the advantage with respect to A is the best action from ST. So if we actually find the action that maximizes A pi, that is the best action we can take if we then follow pi afterwards. So if I tell you, after this time step, you'll be forced to just use pi, which action do you take now? Well, the best action to take is the argmax of the advantage, because that is actually the action that will lead to the largest total reward, if you are forced to follow pi afterwards. Which means that this action will be at least as good as any action from the current policy. So that means that you can safely take this argmax action, and it will not be worse than the policy you would take than the action from the current policy, and in fact, most likely it'll be better. So looking at this, you could say, well, why bother with policy gradient at all? Why not just choose the action by taking the argmax of the advantage? Maybe you don't even need a separate policy. So forget policies, let's just do this. Let's just define a policy implicitly in terms of the advantage function. We'll define a policy as a distribution over actions that assigns probability 1 to the action if it's the argmax of the advantage of the previous policy and 0 otherwise. And we'll actually use this to select actions. If we have discrete actions, we can just enumerate all the actions, evaluate all of their advantages, and take the best one. And that will actually work. That'll actually get you actions that are better than the actions from the previous policy, regardless of what that previous policy was. And that means that you don't even need a neural net to represent the policy anymore. You can just use the advantage function directly. So this new policy will be as good as pi and probably better. So now we've essentially modified our recipe a little bit, where we're still going to generate samples, we're still going to fit our value function, but instead of improving the policy by taking a policy gradient step, we'll simply improve the policy by replacing our policy with this greedy argmax. So we won't actually have a separate network, we'll just choose our actions using this argmax. This is the basis for something called for a policy iteration algorithm. The high-level idea is you evaluate the advantage function of your current policy, for example, by computing the value function and doing r plus next v minus current v, and then you set the new policy to be the argmax policy. And then you repeat. So the big question is, how do you evaluate A pi? You could use exactly the same method we discussed before for Actor-Critic. So as before, you want A pi to be r plus gamma times the next v minus the current v. So let's evaluate v pi of s. Now, we could use samples, we could use the Monte Carlo returns, but right about now, I want to pause a little bit and discuss dynamic programming. I'm going to rewind a little bit and discuss a special case for how we can fit v pi under the setting where we know the transition probabilities, and then we'll walk back to the model-free case where we won't know the transition probabilities and actually recover a very elegant algorithm for doing this. Okay, so first let's assume you know pi of s prime given SA, and both S and A are small and discrete, which means that you can sum over all possible states and all possible actions. In general, you can't do this, but it really helps to derive elegant algorithms under the setting where you can, and then generalize them to the sample-wise setting where you can't. So, for example, you might imagine that your states represent cells in this grid. This is sometimes called a grid world. So you have 16 possible states. And your actions are directions to go, like go right, go left, go up, go down. So you have 16 actions, and you have 4 actions per state. Now, in this case, you can store the full value function v pi of s in a table. Right? There are 16 states, which means the value function is fully determined by 16 numbers, essentially a number associated with each cell in this grid. And your transition probabilities are 16 by 16 by 4 tensor. It's basically a different probability for every one of the 16 states given every one of the 16 prior states and every one of the 4 prior actions. So now you can express an update to your value function as an expected value over the actions from your policy of the reward plus gamma times the expected value of the next time step. And just like before, we can just use the current value function in place of v pi on the right-hand side. And remember, since our policy pi will be this argmax policy, we can just substitute this argmax into the above equation. So it's an expected value under pi, but pi is going to be the argmax. So it's the deterministic policy pi of s equals a. So you can substitute pi of s in there. It's an expected value, but only one action has probability 1. So you just plug that in, and now you have r of s comma pi of s plus the expected value over s prime distributed according to p of s prime given s comma pi of s. So this is a bootstrapped update to the value function. And you can use this in policy iteration. You can evaluate v pi using this bootstrapped update, and then set the new policy to be the argmax policy. And repeat. Policy evaluation, which is just that step 1, just consists of repeatedly applying this backup until your value function converges, and that's called value iteration. Okay. There is an even simpler dynamic programming procedure where we can make use of the fact that the policy pi is not just any deterministic policy, it's actually the argmax policy, and we can actually substitute the argmax itself into the backup. So the way we do that is the following. First, notice that the advantage is the reward plus the next value minus the current value. Now the current value v pi of s is not going to change the argmax because it doesn't depend on a. So that means that the argmax of the advantage function is equal to the argmax of the q function, which is r plus next v. So you can kind of simplify things a little bit that way. You can think of Q in the dynamic programming case, in the tabular case, as just a table with a different number for every possible state and every possible action. And the argmax just picks the entry in every row of that table that has the largest Q value. Basically, the entry corresponding to the action for that state that has the largest Q value. And the argmax gives you the policy. But the Q values themselves actually give you the values. So instead of taking the argmax, you can just take the max. You can just take the numerical entry in that cell in the table, and that will give you the actual value of the corresponding argmax policy. So if you can skip actually explicitly constructing the argmax policy and just directly take its value from the Q function. And this is the classic value iteration algorithm where you compute Q values as the reward plus the next value, and then you update the values to be the max over all the entries for that column, for that row of the table of the Q function. So you kind of skip the middleman. You don't actually need to construct the policy explicitly. You just directly compute the backup. That gives you the Q function in step 1, and then you find the max entry in every row of that table, and that gives you the value. And of course, you can collapse this into one step as v of s is equal to max over a of RSA plus gamma vs prime. Okay. So the policy improvement step is where you take the max, and the evaluation step is where you compute the Q function. Okay. Now let's bring things back to neural network land. Let's talk about actually using neural nets instead of tables. How do you represent v of s? Well, if you represent it as a big table with one entry for every state, this works if your state space is very small, but imagine that your states are like images, right? So maybe you have 200 by 200 images where every pixel can take on 255 values, and there are 3 color channels. That means that the number of possible states is 255 to the 3rd power to the 200 times 200 power. And that's more states than there are atoms in the universe. So you can never create a table that big. And this is called the curse of dimensionality. As your task gets higher dimensional, it becomes completely impractical to store all the values for all the states. So you want a neural net. You want a neural net that maps states to values. And it has some parameters, phi, just like before. But we can use the same idea as in value iteration where we compute these Q values, and instead of simply setting the values at all the states to be the Q values, we'll do the same mean squared error regression. So we'll use the max over A of QSA as our target values and regress onto them using mean squared error regression, just like we had in part 1. So the fitted value iteration algorithm computes target values as the max over A of RSA plus gamma expected value of VS prime, and then regresses onto those target values just like we had in the Actor-Critic portion. Now, we've almost arrived at an algorithm that we can actually use, except there's still a big problem with it. The big problem is in the max. Unfortunately, there's no way to evaluate this max exactly, as written, without knowing the transition probabilities. So this is the problem. You need to know the outcomes for different actions. You need to know what different S primes different actions will lead to find the one that is the max. So let's try to solve that problem. Let's go back to policy iteration for a second. In policy iteration, we would evaluate Q pi and set pi to be pi prime, where pi prime is the argmax policy. And remember, the argmax for A is the same as the argmax for Q, so here I have it written out as the argmax for Q. Policy evaluation consists of repeatedly applying the Bellman backup. So let's not do this. Let's note that we only need the Q function and not the value function, and perform the Bellman backup on Q values instead of values. So it's like a Q value iteration instead of value iteration. Same exact thing, we just, instead of taking the action pi of S, we just take some other action A. And you can fit this using samples. So just like before, you can take your samples, evaluate R plus the expected value of the next Q, which you just do using the single sample that you got, and use those as targets for fitting Q. And we actually still don't, it turns out that we still don't need the policy iteration. We can apply the max trick again, only this time on Qs. So with value iteration, we went from evaluating V pi and then explicitly estimating pi prime to setting the target to be the max, which is the value under pi prime, and then regressing onto that. So we got rid of the policy and computed the values directly. We can do this with Q values also. So with Q values, now we don't actually need to take the max in step 1, because we just need to compute the Q value targets, and the Q value targets are conditional on action, so we don't need to choose the action. But when we compute Y, we take the reward plus gamma times the expectation of the next value, and that value is where we're going to have the max. So we'll take the value not of the old policy, but actually the new policy, of the argmax policy. And the value of the argmax policy is just the max for the Q function. So we'll replace V in our target values as the max over A prime of our old estimate Q phi S prime A prime. So we'll compute target values, current reward plus gamma times the max over the next action of Q S prime A prime, and then regress onto those targets to find the new Q function. And this doesn't require simulating any actions, because now we're just plugging different actions into the Q function, and the Q function is a neural network, so we can plug as many actions in there as we want and observe their outcomes. In fact, this even works for off-policy samples. You don't actually need the samples to come from the latest policy to do this, unlike Actor-Critic, because the Q function is conditional on action. And you only have one network, so there's no complicated policy gradient. All you're doing is estimating the Q function. Unfortunately, this algorithm loses some convergence guarantees. We won't have a chance to talk about it in this class, but these kind of theoretical issues would be discussed in a graduate level reinforcement learning course. So just keep in mind that the Q-learning algorithm theoretically is a lot less principled than policy gradient when you use function approximation, and in practice what that means is that we have to work harder to tweak the algorithm to get it to actually work well. Okay, but here's the full fitted Q iteration algorithm. And I'm going to describe the algorithm on the left side. On the right side, I'll describe its parameters. So step 1 is to collect a data set of states, actions, next state, and rewards using some policy. So you might actually make rollouts. And here you have to choose how many samples to collect each time. Step 2 compute the target values for those samples by taking the reward plus gamma times the max over the next action of q phi evaluated at the next state and the next action. Step 3, solve the mean squared error regression problem by actually fitting those target values. And what you're fitting is a neural net that takes in a state and an action and outputs a real valued q value. It has some parameters phi. And you have to choose the number of gradient steps to take when fitting, and you have to choose how many times you update the target values and refit before you collect more data, the number of iterations. So this is a basic fitted Q iteration algorithm, and it can serve as the starting point for practical deep Q learning algorithms that we could actually use in practice. We're not there yet, but this is the basic scaffold. All right, so we'll talk about the full Q learning method in the next part.